Hello everybody. In today's class I would be demonstrating how to do a layout in Cadence and also how to do a DRC checks after doing the layout. DRC checks stands for design rule checks, and then LVS which stands for layout versus schematic. Okay. Before that you need to go through this. You can go to my web page, and in the courses you have a course known as VLSI design. Okay, and there if you scroll down you will find a lecture on layout. Okay, this is lecture 11 where layout of static CMOS. So if you click on that, so you have the PDF as well as an embedded video which will give you the theoretical background for doing the layout. So if you go through this video and understand the concepts of layout, then it would be better for you to start doing layout in Cadence. Okay, first the theoretical background, if it is clear, it will become more meaningful for you to start doing layout in Cadence. So I would recommend first you go through this video. Okay, go to my web page sanjayvidyadharan.in, and then you have an courses tab, and you can select the VLSI design course and come down to lecture number 11, which is layout of static CMOS circuits. Okay, here I have drawn a schematic of an NAND 2 implemented with 45 nanometer CMOS devices. Okay, so these are two 45 nanometer NMOS, and these are two 45 nanometer PMOS. So I have put one ground here. I have named this particular this is an port, right, an output port. So I have put it as ground 2, output pin, sorry, so output pin as ground 2. I have taken input output pin. Okay, so this is VDD2. I have just given the name as VDD2. Okay, so that is the pin for the VDD. Two input pins A and B, and one output pin as Y. Okay, so these are the external pins. Within this, if you see here, there is no voltage source supply or things like that. Okay, there is no ground and all. Okay, this is an just a schematic in which you have pins and the devices. Okay, so you have 1 2 3 4 5 pins, and then you have 4 devices. Now if I see the sizing of this, like if you go through my VLSI lectures, you will find that how the sizing has been done here. So normally an unit inverter will have the minimum width for an 45 nanometer device is 120 nanometer, right? And a unit inverter will have NMOS 120 nanometer and PMOS as 240 nanometer, because PMOS is considered is slower than the NMOS because of the holes, lesser mobility of the holes. So generally we keep the width of the PMOS twice that of the NMOS, so that the rise time and fall time is same. In this particular case, now I am just designing a NAND gate which has an delays equivalent to that of an inverter, and for that reason, since I have two NMOS in series, so instead of 120 nanometer I have taken it as 240 nanometer. Now since the width is doubled here, so obviously the resistance will be half, and the total resistance from here to here will be equivalent to that of an single unit inverter, right, 120 nanometer. So I have taken 240 nanometer and 240 nanometer here. Okay, whereas if you see the PMOS, they operate in the worst case delay. In the best case delay, they operate in parallel. Okay, but we need to cater for the worst case also. So in the worst case scenario, only one PMOS will drive the output voltage to high, taking supply from the VDD. So that is the reason we keep the width as 240, right? For a unit inverter, the PMOS has to be 240, and here there is only one PMOS. There is not two PMOS coming in series or two PMOS coming in parallel also. Okay, we are not taking the parallel combination because that is that can happen, but in the worst case scenario only one transistor also can be there, and that is the reason we have taken it as 240 nanometer. So let me just click on this device and go to Q, so that you know what this is. GDPK 045, PMOS 1 volt, and excuse me, length is 45 nanometer. So all the device length is 45 nanometer, and total width is 240, and finger width is also 240, right? So same is the case for the NMOS also. If I go to the property, if I press Q out here, so I see that okay, length is 45 and width is 240 and single width. Okay, so this is about the schematic, and from the schematic now I need to make an layout. So I go to launch out here, and then layout Excel. Okay, so this will open another window in which, okay, it create an new. Okay, so it says, okay, with the same name, layout. So that is the layout way. So let me just minimize this schematic, and let me just open the layout window. Okay, this is the blank layout I have inserted. So let me pick up the components. So I press I, so I browse. I am going to the GDPK folder. And I'm going to take an NMOS out here. NMOS 1 volt, right? And I'm taking the layout. I'm picking up the layout. Okay, so hide. Okay, so view. Okay, so this is the NMOS. If I press Shift F, I'll see the device. Okay, so okay, now what I'm going to do is I'm just scrolling it. Yeah, I'm going to the properties, right? Now parameter. I want two NMOS, right? And they're connected in series. So I am going to take an 240 nanometer total width, and I am taking fingers as 2. Okay, and also so this doesn't have the tabs, so I would want to have the tab also. Body tie type. So detached. Okay, so I am going to select the detached type, and I am going to have, because this is going to be the NMOS, I am going to use an bottom tab, and I am going to remove the left tab here. Okay, so I am going to press OK now for this, and I am going to put it now. Okay, now you see that this is the NMOS which has come, right? Now and let me have a PMOS also. So let me just copy this device and put it here on top. Yeah, so okay, so now I have an NMOS. Now I have an This is also an NMOS, so let me change the properties to PMOS. So I am going to the attribute first. So here I am going to make it as PMOS. Okay, and so now this has become an PMOS. Right, now I'm going to the parameter. Again, finger width is 240, fingers is 2. Right, let me this is detached, and instead of bottom, now I am going to have the tab on the top. Right, okay. View, zoom to fit all. Right, okay. Now the widths, lengths don't appear to be same, so let me just check it once. Parameter, length, finger total width is 240, fingers is 2, that is okay. Okay, the problem is understand. The one has got pasted over the other. Right, okay. Now I have the NMOS and I have the PMOS out. This is how a layout of an NAND looks like. So what I have done is, let me show you this. Okay, what I have done. So I have taken this from the GDPK. I have taken an NMOS transistor whose parameter I have set it as 240 nanometer as the width, because I require 2 transistors. Width is equal to 240 nano, and that is why I have taken fingers as 2 and the finger width as 240. Okay, and then also if you see these tabs out here, so in like 45 nanometer technology, these tabs come along with the transistors. In certain versions or technology files, you won't get these tabs, so you might have to externally pull in that tabs and also keep it here. Right, now the position of this tabs also can be adjusted here. Here it says it is in the bottom, so I have kept it here in the bottom, these tabs. Okay, if I keep it to the left or right, so these tabs accordingly they will get positioned on the right hand down. So I just want it in the bottom out here, so I have taken that bottom out here. Right, so this is the transistor which I have. Now similarly, PMOS, if you see here, this is the PMOS which I have used out here. Right, if I go to the properties, you will find that I have taken 240 nanometer, 2 fingers, again under the same PMOS has been taken here. Right, and here I have taken the tab setting to be top, so that I get these tabs on the top. Okay, not in the bottom out here. So that is the only difference. Okay, so having made this, okay, now the problem is to connect these two gates, right? So this is A input and the B input. So I have used a poly. So there is a poly option available here, and then I created a rectangle out here, right? So I can create a rectangle. So the shortcut for rectangle is R, and then I created a poly. So I can create a poly link out here. So if you see here, this poly, and then you have these shortcuts of S to stretch it and just match it. So now you have these connections out here. So copies again C out here. So let me copy this C and I have put it here also. Right, now I want to take a metal connections inputs A and B. Okay, so what I do is I go to create via. Right, so I have metal 1 to poly vias. Okay, so I can create one out here, one input here. These are going to be the inputs, right? So these are the kind of vias. So I have to connect these two also. So let me move this, right, and place it here instead. Right, so this is how I place these two vias here, metal 1 to poly vias. and then I can go and create, I can put some more metal out here. Otherwise the DRC would say that this metal 1 area is below the permitted levels. So that is the reason I'm going to put one metal layer. So I have to first select the metal layer out here, and then I create a rectangle out here. Yeah. So I create a metal rectangle here, and I create a metal rectangle here. R is the shortcut for rectangle, so I press it. Okay, and I put one more metal rectangle here, right? And here I can do create, right? And then there is an option of pin, right? I need to create in pins, right? So A, right? So similarly I create pin, okay, B, right, height. So I can create a pin out here, right? So I have created these two pins. If you see here, if you go to the properties, it say no, terminal name is A, right? So I have created these two pins. I have interconnected the gates, and I have put one via, and I have created these two, right, layers, right? Now I have to I have to create a ground from here to here, right? So I can create a ground by just pulling in metal layer out here. So right, and then I make one more metal out here. So that this is my ground, right? So I then I can create a ground pin out here, right? Similarly, I can make connections between. So there has to be these two are in parallel, right? So I need to make an VDD. So from this, okay, I make a metal layer out here. Yes. Okay, so I have connected this to the VDD out here, right? So this has become a VDD, and now also both are them in parallel. So I can connect an wire out here. I can bring it here. Sorry. So I connect these two, and now these two also, since they are in parallel. Here I have given VDD, but these two have to be interconnected. Okay. So what I can do is I can go for a metal 2 also. Okay, I go for a metal 2, and then I create a metal 2 layer out here. Right, so the red color one which is here, that is metal 2. Right, now I have this is metal 2, but this portion have to be connected. So they are metal 1. If you see, that already metal 1 is there. So I need to create, okay, via, okay, a metal 1 to metal 2 to metal 1. Okay, create. So I place one via here and one via here. Now, so now this metal 1, okay, which is the the source is connected. Drain of this transistor has got metal 1, and I have put an wire here, so that has got connected to the big metal 2 which I have placed it here. Again I have put one more wire here, so the drain of the next transistors. Now these drains have got connected in parallel. Right, now the source are already connected to VDD. So this is how you make the layout. Okay, so let me delete it. F. Okay, now I can go to Asura. Okay, and then I can run a DRC. Okay, so once I run it, okay, it will take some time. So this DRC run is over. If I it says do you want to see the results? If I say yes, it says no DRC errors. But if you have not done the layout properly, if you have violated any of the DRC rules, then it would say, okay, the DRC is not. So let me show one example. And so I am pressing S. So I am making this wire length thin, right? So now you will say that this is not permitted. So there is a minimum length criteria for this wire. So let me run the DRC again and see what happens. Asura and then run DRC. Okay. Okay. So now I am running the DRC again and I can expect there will be a DRC error. Okay, the run is over. Now if I say it says, okay, now it gives an error that metal 1 width must be greater than 0.06 micrometer, right? So if I have to click it here, so see it's being highlighted out here. So I know, okay, so there is a DRC error, so I need to rectify it. So let me stretch it back to the original size. Okay, similarly, whatever mistake you do, this will point out. Okay, this was the minimum width. So let me show you one more error where I have kept these two wires close to each other. Okay, so this was the NMOS. Okay, these are two NMOS in parallel. I had grounded one terminal. In between there was this is the drain of the first transistor and the source of the second transistor, so that terminal. So you can't leave it open out here like this. Okay, this is the, so here it will say there is a metal 1 width is very less, so I need to put some extra metal there. So I had earlier put some extra metal out there to meet the DRC, and now I have stretched it. Okay, I have brought it very close to this wire out here. Right, now it will give me some error. So let me go to Asura and again run DRC. Okay, let me rewrite this. Okay, now see, we can see what's the problem. Okay, the DRC run is complete. So let's see. It says, okay, metal 1 to metal 1 spacing. Okay, now if I zoom in, it is highlighting here. That means this metal 1 to metal 1 spacing is not adequate. Okay, so that's why I again resize this back to this, right, and then off it and then Asura run DRC. Okay, so I have shown you now two kinds of errors. In those errors I have shown what happens if you have kept the size of an wire less than minimum permitted, or if we have kept the spacing very close to each other. So these kind of issues will be there. Okay, now the DRC should be all right because I have reverted, so no DRC check. Okay, no DRC errors. While opening the DRC run, you got to be careful with the rule file path. This has to be set correctly. So my DRC in my particular thing, it is I am using 45 nanometer and Asura, and there the DRC rule file is there. So I need to give this path. Okay, I also have need to specify the technology. So these depend on the system on which you are working and where the files have been placed. You need to set it. Okay, so once the DRC check is done, then you can go for LVS. LVS is nothing but checking this layout with respect to the schematic. Okay, layout versus schematic. LVS stands for that. So I do LVS. Okay, let me check. Okay, so it's going to do an LVS run now. right? So it says no, everything is fine. They have been matched properly. No cells have any issues out here, right? So if you have done a mistake, then accordingly you will get some errors. Okay, so let me show you some errors also. Now if you see here, I have connected this NMOS and this PMOS, right? These two PMOS, they were in parallel, and then from the parallel I have connected it to the top of the NMOS out here, right? So let me move this out here, right? Now I have moved it here. Now I do an Asura run LVS. Okay, so if I do that, so most likely I will get an error out here. So you can see that error, and accordingly you can verify what is wrong with your circuit. It will also suggest some things to do. So now if you see here, the error has come here, right? So it says ki one cells has not divided, had a net mismatch and a pin mismatch, because since I have moved this wire out here, okay, now this pin is not connected anywhere out here. So these errors have come in here, right? So now reading these things, these error log, okay, you have to figure out, okay, what could be the reason. Okay, so sometimes it gives some suggestions also, so that this would be a better match and things like that. Okay, so seeing these errors, and we can do the necessary corrections, and finally till the LVS is cleared, right? I move this back now, right? Let me move this back out here, and I align it here and leave it here, right? And let me show you one more thing. Now this is the pin, right? So which we have put, so output pin, right? So let me move this pin here. Okay, this is the pin. Okay, I have put a label and a pin both, just for more visibility. So let me move this view, zoom to fit all. So now I have just removed the output pin, okay, which was here. So let me run an Asura run LVS. Okay. In the previous case, when I removed this one, there were multiple errors, right? Because there was a pin mismatch and a cell net mismatch. Now there is only a simple error that there is one pin mismatch. Let's see what the kind of error it is giving. Right? It says one cells had a pin mismatch. Okay. So now if you can go to the if I press OK out here, it says NMOS schematic, right? And view LVS error report current cell. If it says okay, it gives is like the number of NMOS, PMOS, they are all matching out here, right? So it gives a detailed report. So if you go through this detailed report, you will know what is the problem out here. Now it says out here, right? Schematic, there is one pin. Layout, one pin is missing, which is Y. Okay, so in the schematic it is there. In the layout it is not bound by pin. So all that error, it will check the error and it will tell the error. So if you go through the error summary, so you will be able to come to know what is the kind of error. Okay, once the error comes out, you press OK. You will go to an debug. Here you have the options. Okay, show view right, log file and error report and all cells, right? Cell mismatch statistics and all these things are there. So you can view these things. Okay, and then See, this is the unmatched pin, on-bound pin. So here it clearly says pin Y, which is there in schematic. It is not there in the layout because I have moved that pin here. So this is how we can do that correction. So I can now move back this pin and put it back out here. I put this back here. One is label, one is pin. Okay, so that is why two things are seen here. Then I go back to Asura, and then I do an run LVS. Okay, if I do that. Now you see there is no errors, everything is matched. Okay, 0 cells have device problems, 0 cells have label short problems, 0 cells have label open problems, and no mismatch. Okay, 0 device mismatch, 0 pin mismatch, and 0 parameter mismatch. So that means the layout and the schematic are perfectly matching. Okay, so that's all for today. In the next class I will tell you how to extract the parasitics and do a post layout simulation. Thanks a lot.